Hi guys, welcome back. One of the core bottlenecks in building agentic RAG or deep research pipelines over financial documents is their complex layout. These documents have all sorts of tables, nested tables, figures, diagrams, tables that span across pages and hundreds of pages. So these PDF documents, it's extremely hard to parse them correctly. While there's no dearth of PDF parsers of all kinds, almost all of them have a hard time parsing arbitrary PDF files, and in particular these financial documents like SEC reports. Recently, we've seen the rise of LLMs to parse these complex documents. LLMs offer a very unique advantage in that they understand both the document layout as well as the content. And LLMs are now regularly used to convert these complex documents into markdown. So markdown is the chosen output format because it preserves a lot of structure in the original document from the original document as well as the content. In this video, we'll examine how document parsing plays a crucial role in these agentic RAG or deep research pipelines. Document parsing, PDF document parsing, involves extracting different sections correctly and the content of the table, the numbers, and we'll discuss how specifically this is example from the Llama Cloud, Llama Parse repository, which deals with this Fidelity Multifund Annual Report. This example of a really complex document and representative of several such documents. And we're going to see, the goal is to answer a bunch of queries over the documents which are non-trivial. And so the goal in this talk is to define a bunch of high-level operators that are common to parsing these documents and see how each of these operators are implemented using LLMs. So this notebook will go through the details. So before we jump into the implementation, this is the high-level workflow that we want to implement. The original document is here, which mentions several funds and their details over multiple years. And our goal is to extract and aggregate information over these multiple funds, and it's not visible. It's so if there are funds which are 20%, 30%, they categorized by these percentages, and we want some common details, features to be extracted from this document about these. And this information is spread across the document, so it's not straightforward. The same fund is repeated several times in the document. So any simple chunking strategy it will be extremely ineffective here. So the overall strategy is that we need a document splitter that finds where each of the funds are and the multiple places where they are. So we'll have to find the consecutive set of pages where each fund is specified. Once we localize the fund, then we extract the data. So there are tables here, we have nested tables. We extract the data in terms of a JSON format, and these JSON objects are structured, a result of structured extraction. The output is a bunch of fields common to all of them. And once we get this in structured representation from these unstructured documents, we can then combine together in whatever format, CSV or data frame, whatever format. So this is the high level overview, and we'll see how each of these steps, particularly the split by fund operator, how it's implemented. So let me scroll down to the output again so that we have a quick look over what kind of output we're expecting and what queries we want to ask. So this is the output, the column fund name with the different fund categories, These are the fields we want: target equity percentage, report date, equity percentage, fixed, so on. So these are the fields that we want to extract from the which are the funds. And as I said, it's all this, the information is distributed across the document. Once we have this table, we would like to ask queries like, yeah, show me all the funds where actual equity allocation is more than 5% higher than the target, right? So you can see that this is a filter query, and which also involves an aggregation. So we want to, yes, this is the pandas code that will get us the filter. We can ask, yeah, so this is, I think there was another query, but yeah, so this sort of query needs to have all the information in a table format. You can't go over looking for actual equity allocation and the target allocation percentage uh, at the time of the query. It's good to have this information pre-computed, right? So how do we get this table from this document? So let's start looking at the parsing. Yeah, so it's useful to view parsing as a bunch of operators that are, yeah, so a bunch of operators, and there are quite a few, but the details are in how these operators are implemented using LLMs. The first operator that's generally used is parsing the document to markdown. And these LLMs are used for this stage also, but in this case, it's handled largely by the Llama cloud. The split by predicate is the most interesting operator, and this roughly corresponds to chunking. Usually, we chunk by section headers or by maybe table boundaries, or just by paragraph in the simplistic case. The split by predicate operator generalizes all of those cases, and for example, you split by page. Pages are separated by markers. You can use a regular expression to to split by page. But in this case, what we want is to split by fund names, and that's very interesting because first we need to figure out what are the fund names. They're not given by the user in the beginning, and once we figure out the fund names, we want to split by the splitting by a particular name is a very complex operation. The name might be mentioned at several points in the document, and there might be overlap in different names. So to know where the boundary of a name starts and ends, or a name header, where does it start and end, that section is very hard to find that out. So that's what is unique to uh, this particular parsing implementation. So and the final operator is extract to a particular format. It's the what is called a structured object extraction uh, from text documents. You could convert it into a JSON format. You can convert data frame, and the JSON you could specify a structured object that the output should look like. So three key operators, and the most interesting split by predicate. If you can implement the goal is to show how this is implemented in this case, and it would be you would find it easier to generalize it to other documents once you understand this predicate. Okay, so let's dive in. You get the fund, it's hosted somewhere, Fidelity. Okay, and then the first step is, uh, yeah, just call Llama Cloud Services to convert in Markdown, uh, Markdown with sections and so on. So this doesn't need a deep knowledge of the document. It needs to understand the headers and headers, subheadings, and the table structure. So it's handled behind the Llama cloud here, but you can use tools like Docling to do the similar conversion from PDF to Markdown. And the operator split by page is passed, that creates markers where the page ends. Good. So once we have these marked down, we can still not issue our queries directly over these documents. I mean, if you could pass in the whole context to the LLM, the whole document, markdown document, but uh, there are many cases where the LLM can either hallucinate information or come up with partial information, partial results. So we are adopting a more controlled approach to parsing where we localize where each fund is and then we extract content from it. So extremely, I would say, um, extremely structured and controlled approach. Um, so how do we define the split function? We remember we want to go from the document, the markdown document, to where each fund is mentioned. Now we don't know the fund names first of all, okay, and so we have to first extract the fund names, and that's a very suitable task for LLMs who go over the document and find things that look like fund names. And this is the prompt, split category prompt, that find the categories that are correspond to the fund names. Okay, so for instance, if user asks find all top level sections of archive paper, then sample output would be um, this one, right? So there's a quick example how to, it's a pretty generic prompt that will get you the categories in the predicate. Um, so yeah, go down. Implementation is pretty straightforward. The magic is just in the prompt, and the LLM follows the prompt well. For the document, we'll find the section. These are the categories, right? So we have got all of these 1, 2, 3, 4, 7 categories, 7 fund names. And now once we have these fund names, then we are going to split using these fund names. So that's where a lot of interesting stuff, and you see how the complex the complex layout of the document. All right, so let me just again, the magic is in the prompt here. The split tree, there you can have, yeah. You're given a chunk of the document text at a time. You're responsible with determining if chunk of the document text corresponds to beginning of a split. So that is very interesting about this prompt. It doesn't take the whole document in one go. It takes a page, which we have already found, and only determines if the fund that we want, the category, is there in that page or not, whether it starts or ends or yeah, or it's not there. So that's the crux of this prompt, and then there are a bunch of I would say guardrail like rules where you should only extract if the split of document contains the beginning of a split and not if the document text contains beginning of 2 or more splits, there are multiple sections on a single page, then return all the splits in the output. So there are several nuances on top of it, and they've done a good job thinking about all the boundary cases and putting them down in the prompt. So it's a very useful prompt. And the output. So again, with this prompt, we specify a bunch of structured objects. These are inherited from pydantic base models. So we want these outputs after parsing, we want the output in that format. A bunch of other details, but let's just look at the output here. Yeah, there's another prompt, find and split by the main funds of the store. They should be listed in the first few pages. But before going there, let's just look at the sections that found after splitting. Yeah, so for the asset manager 20 class category, a bunch of from 2 to 13 and then 93, 94. So you see that there's one location, it's all across the document, there are multiple mentions of each of them. It finds a sequence of contiguous pages where the fund is start and description ends. Similarly for each of these. The last part is very interesting. You see that there is a bunch of pages in the beginning which are contiguous, but then there are these sporadic pages. What happens here is in these pages, especially around 100, let's see, this is a page 104. What happens is that asset manager 50%, asset manager 40%. So these funds are mentioned very quickly one after another. So on the same page, there might be, let's see, I think there might be, same fund mentioned on the same page. So both the beginning and end of that category lies on the same page. And the more difficult case is that the information overlaps across multiple. There's no clear, it doesn't align with page boundaries. That's a very tricky case. So yeah, so it does a pretty good job of extracting roughly where the fund is, and thankfully that the information, the boundaries that it extracts is good enough to answer the queries. It's not perfect, let me note that it's not perfect, but in the case of fund overlapping descriptions and not aligning page boundary, it's really hard to define a very systematic output format. So this prompt uh, does a good job in finding the split pages and then splitting the funds by these contiguous sections, pages. Right. So once we get these sequence of pages, then we can only extract these pages, and that ensures high recall. Those are the pages out of hundreds of pages where we can from 70 to 120 for 85. That's all we need to look to get all the information on. And that makes the process much more controllable. It gives less context to LLM. LLM can have better performance for that. After that, the process is of extracting a table. Let's look at the document. Yeah, so from this, we split by fund, we get these sections, and then we do a data extraction for converting JSON. This is a relatively standard and straightforward. We have narrowed the pages, so and we are looking for specific set of information. So all that is specified again as a structured object. Fund name, target equity percentage, report date, equity percentage, and all of them have a description. So this structured object helps LLM figure out what to look at among those pages and extract this information. Right, and so we run the extractor with the output this and do some aggregation of it. That's pretty standard, so I'm not going into details of it. And we get this converted into CSV, and finally we get this in-memory data frame, which contains all of these columns, which columns corresponding to fields of the structured object. And that is good enough to answer the rest of the queries. There's also more details about the workflow, asynchronous pipelines that you can build with each of these steps, and they can be coordinated in asynchronous fashion. But that's besides the parsing, the code parsing detail. This is particularly used to scale up to large documents. Once we have this, then I'll go back and again, yeah, we want to find the most return efficient fund. For that, we do a simple pandas operation, and we get the best. The first one, 20% is the best one. And again, how far do allocations? So these natural language questions correspond to simple pandas programs, which can be implemented over the table. And again, like this example shows, this is more complex queries where where a more complicated filter needs to be defined. And again, there are several ways of converting a text query to pandas or a SQL query. This is one of the examples, and this converts. Llama index supports that, converts it into this query, and you get this output, and that's presented by that. So that's it. That's the high-level overview of how parsing can be implemented by using LLMs. Coming back to the core operators again, LLMs are used to parse an arbitrary complex document, PDF document, to markdown format, which preserves a lot of structure. You separate them by pages, and then you need to implement a split by predicate. This is a very powerful powerful operator, and in this particular example, we wanted the split by fund, and we saw how we first figure out what the fund names are and then split by predict by the fund names, and finally extract the details to JSON format. So that's it. It's very, these operators are quite universal, and if you're working with financial documents, you would be implementing some combination of them, specifically the split by predicate.